Okay, 5.7, talking about the fundamental theorem of algebra. And you may have noticed what the fundamental theorem of algebra says just in all of your experience finding zeros. For instance, if you had x to the third plus 2x minus 5, 2x squared minus 5x plus 7, something like that, how many zeros might you possibly, maximum, find in this polynomial? Well, at most, you're going to find this many. Whatever the degree is, that's the most you're going to find. So, we'll just, fundamental theorem says, degree tells us maximum number of zeros. And this would include if we got imaginary numbers, right? Including, or what we call complex numbers. A number with I in it, including complex zeros. Okay, so if we were to find out the zeros and find out that, you know, we got 2 plus or minus I root 6 over 3, then, you know, that those two, plus and minus, those two would be solutions, right? And we would include that in there so that the fundamental theorem of algebra would be correct, that this is the maximum number of zeros. So if we change it a little bit, and let's use this as a example. Okay. Well, let's find the zeros of this expression, of this function, let's say. We'll factor it. We get x plus 2 times x plus 2. Right, that's what this is going to factor out to be. So we get x equals negative 2 and x equals negative 2 again. Okay, so we're changing up the fundamental theorem of calculus a little bit to say that whatever the degree is, that's exactly how many zeros. We'll always get this many zeros if we count repeated solutions as many times as they show up. So if we count this as not one solution because it's just negative 2 twice, but we count it as negative 2 and separately negative 2 again. Okay, so we'll talk about it more in these terms of exactly the number of zeros counting complex zeros and repeated zeros. So if we always count the complex zeros, you know, the imaginary ones, and ones that come up more than once, even if it came up 3 times in a different polynomial, then we would say that the degree is exactly the number of zeros that we should expect to find. Okay, so that's the way we'll talk about it more, like this. It's a corollary of the fundamental theorem of algebra. Okay, and just a couple more things. If you had a polynomial, okay, you know, it's like a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus all the way down to a sub 0, that being the constant term. Then if you were to find that, say, 2 plus I is a 0, you just found that to be true for some reason. It fell out of the sky, or you just had a vision or something. If this is a 0, and all of these coefficients are real numbers, which that will always be true for, I don't know, that even in my calculus class up through there, I don't think we deal with polynomials that have anything but real coefficients. So if that's true, if you have a polynomial with real coefficients and you find that 2 plus I is a solution, then 2 minus I is a solution. Its conjugate is a solution. Okay, let's talk about complex conjugates for a minute, because this is a complex number, this is a complex number, and they're conjugates because we change the plus to a minus, or the minus to a plus. They're conjugates. So what about 5 plus 3i? What would be the conjugate? 5 minus 3i. How about 16 minus 3/2 pi times I. It would just be 16 plus 3/2 pi times I. How about just I? What would be the conjugate of I? It would be negative I. Okay? So these are what you call complex conjugates. And for all the polynomials we'll ever work with, if this is 0, so is this. If this is a 0, so is this, and so on. Also, we have what's called irrational conjugates. Okay, that would be a 0 that you find that is irrational, such as, and usually these will come up from using the quadratic formula, and so will these. So how about 3 plus root 2, then 3 minus root 2 would also have to be a 0. Okay, this is for, and again, I don't think I've ever seen an example of a polynomial that wasn't like this, but this would be a polynomial that has rational zeros. Okay, so you don't see any square roots of 3 or pi or anything as a coefficient. I think I said rational zeros before. It has rational coefficients. I don't think that you've ever seen pi or the square root of 3 as a coefficient of a polynomial, right? Something in front of like x squared. You never saw pi or the square root of 2 in front of x squared. Okay, so just assuming that that's the case, assuming that we have, this is assuming a polynomial with rational coefficients. This one's assuming a polynomial with real zeros, or real coefficients. See, I did it again. Whoa, with real coefficients. Okay. So assuming that you have a polynomial with rational coefficients, which has been every polynomial we've ever done, if this is 0, so is this. So let's talk real quickly again about complex or irrational conjugates. So if 5 plus root 7 is a 0, so is 5 minus root 7. If, let's think of the weirdest one, pi, that's an irrational number itself. So let's do 13 minus, let's do 5/3 pi root 3. Then 13 plus 5/3 pi times root 3 is also a 0. So you just, we typically will write whole number first, or rational number first, and then irrational second. So we'll just change the sign on that rational number, and we have what's called the conjugate. So the way that's going to play out in our problems is they'll tell us one of these is a 0. We'll have to remember to assume that this is a 0 as well, and work from there. Okay, and you'll see that specifically in the sample problems. So stay tuned for that. Thanks for watching.